Hello, hello. Welcome, everyone. I'm Quinn. I'm a coach at Major League Hacking. It's so great to have you all here. Today, we're going to be looking at how to make better decisions with uncertain data. This is super exciting, and I think a super important skill to use at a hackathon. So as we look forward to the new hackathon season with season launch week this week, I hope it's going to be really useful for you. And if and when you attend hackathons over the next year, you're going to learn loads of things that you can put into practice. First off, I want to say, please do check in if you haven't already. I'm going to pop the link in the chat. Let me just, there we go. I'm also going to put it up on screen. So you can check in at this link. If you check in, you get points, you get swag, all the good stuff. Make sure to do that. Yeah, we're going to be learning about how to deal with data. We're going to be, well, I'm going to be using VS Code. You can see I've already got it up here. You can use whatever you like. Really, we're just using Python. It's nice and beginner friendly, and we'll talk a little bit about Bayesian statistics. Really, that's kind of the focus of this session. So if you're new to that, don't worry. We'll go through it nice and slowly. And if you already know what that is, great. We're going to build some cool things using those principles later. So yeah, be sure to check in and then pull up your IDE of choice, and we'll get started pretty soon. I'll maybe give it a minute or two more before we dive into it. But yeah, let me know how many streams you've been to this week, how you're doing. I'd love to hear what you're all thinking, what you're excited for as well. I think the season mascot's due to be announced in a couple of days, which is super exciting for me. I love season mascot. Super excited to see what it is. I'm gonna put some music on as well. If the music's too loud, let me know, or too quiet as well. Might turn it down just a little bit so you can get a nice background vibe going. Perfect. Awesome. Cool. And as a heads up, I have all of the things that I need up on my screen. So that means if you have questions or comments, you can send them and I will be able to read them. And that's whether you're on YouTube or Twitch. So I'll be keeping an eye out for your comments and questions if you have any. And yeah, you can kind of ask away. Also, as a heads up, if I'm looking down here, it's because it's where I've got my notes and things. So don't think I'm ignoring you. I'm always paying attention. And actually, maybe to begin with, it would be more helpful for me to share. Let's see, can I? Yeah, okay. Let me share a different part of my screen. I would like to share. You can never find the thing that you need when you're looking to share, hey? Yeah. Moving all the tabs around. In truly typical form. I've got some markdown notes that I want to share. They're not showing up. We might just move on from that. Let's see if I can get it to play ball. Not looking good. Let's try again. Okay. Here we go. Perfect. Okay. So hopefully you can see these notes up on the screen here. These are just some notes that I wrote up about like what probability is, why we kind of care about it, all of the different keywords that we're going to be using, and a little bit about Bayes. Bayes is this guy who came up with Bayesian statistics, which you've probably heard. Probably most of you are familiar with machine learning. And if that's the case, lots of kind of machine learning algorithms and so on use lots of kind of Bayesian principles. Oh, we're jumping all around now. Where are we? It's like a spoiler for all of the things that are coming up. Where have my notes gone? Okay, there we go. It's just jumping about. Don't know what's done this. Let's start this nice and high. Okay. Fixing the notes live. There we go. Okay. So yeah, we'll talk through a few key things, and if at any point I'm going too fast, tell me to slow down. I know like some of this probably might not be very familiar to you if you haven't done much statistics. Also, this will be entirely new to you. But I think it's super important. And I see so many projects using lots of data without really considering the kind of inner mechanisms and behind the scenes things that maybe they should, the assumptions that you make when you're dealing with data. are very impactful, and so it's worth bearing in mind. So first off, I guess this is maybe a good question. Maybe you're thinking like, oh, what's the point of this? Like, I'm kind of, I tuned in because Quinn is cool, but I don't really care about statistics and what this stuff. Like, why probability at a hackathon? Like, what's the connection? And actually, the thing that I would suggest is that when you're using data, there's going to be things which you're not certain about, right? You're maybe not 100% sure of something, or maybe you even have like an idea ahead before you look at the data of something which you think to be true, right? So a really obvious example is, let's say you've got a dice and you think it's a biased dice, right? You think, your mate gave it to you and they're a bit of a prankster, a bit of a joker. And you're like, I think this dice probably rolls, more on the low end than the high end. You've got this what's called a prior distribution, or like a prior idea, an idea before you look at any of the dice rolls that it might not be fair. And then we might roll the dice out a load of times, and then we would track how many times each face on the die comes up. And we might go, oh yeah, actually, like, it is a fair die. That's great. Or we might go, oh no, it's like bias and it only rolls low numbers. And these kind of like principles, while this is obviously like a very toy example with a dice, turns up in all sorts of places, and we'll see an example later for like a really practical kind of use case, even in the kind of like corporate world. And so when we start thinking about probability, there's a few things that we want to maybe talk about. Experiment, I think probably most people know what this means, but this is when you do something and you're not certain about what will happen afterwards, but you can collect some data, right? So, and then you've got an outcome, right? So tossing a coin is another good example, and your outcome for tossing a coin is heads or tails. I guess you could land it on the side, but for the sake of this, we'll assume that the coin lands flat. And then you have an event, right? And this could be any collection of these outcomes. So your event might be getting even number of heads, or getting like twice as many heads as tails, or any complicated number of things. But a simple one is just getting heads, right? If you flip a coin and then you get heads, great. If you flip a coin 10 times and you get 5 heads and 5 tails, that would also be an event. So those are some kind of keywords. And then there's this idea of a probability distribution. And these are kind of like functions, but what we're basically doing is we're saying, okay, there are all of the different outcomes that can happen, right? On a dice, you've got 6-sided dice at least. You can roll 1, 2, 3, 4, 5, or 6. And normally, you'd assume that each of those are equally likely if you've got a fair dice. That would be a uniform distribution. The probability of getting each number is the same. But you might have a probability distribution where it's not uniform, it's maybe not fair. So for example, you might say, okay, I actually think the probability of like getting a heads on my coin, maybe it's an unfair coin, the probability of getting heads is 0.8 and tails is 0.2. So you've got to bear that in mind as well. You can see we've got some hellos in the chat. Welcome to anyone who's just joining. We've got Adam. Adam is a friend of mine. We've been to many hackathons together. Great to have you all in the stream today. Yeah. So for anyone who has just joined, we're talking about probability and why we care about it in a hackathon. And we've come across this idea of a probability distribution, which is where we're saying, okay, for all of the different things that could happen, we've got some likelihood, some guess on what we think, the probability is for that outcome. So like I was saying, if you kind of thought, okay, maybe heads are more common than tails, you might have your heads at 0.6 and your tails at 0.4. But remember that it has to add up to 1, right? And that makes sense because you can't have, if you added them all up and it added up to more than 1, then you've got, something confusing going on, right? That would be an unnormalized probability distribution. But in this case, when you consider all of the different things that can happen and you say, okay, we're going to collect them all together, the probability of one of them happening is 100%. And that's why it has to add up to 1. So 2 different flavors of distributions. We've got discrete ones, and these are the ones that we've kind of just spoken about. So if you roll the dice, there's 6 different things that could happen, right? There's 6 discrete, like, segmentable outcomes. And, we could say this is finite outcomes, tossing a coin, right? 2 outcomes, or counting how many people go into a newsagent's shop in an hour. That's also discrete. You can't have half a person. And then you've also got continuous distributions, and the very common example is human heights, right? If you've modeled all of the different heights, you can be 170 centimeters, and you can be 170.3 centimeters, and as much as you've got resolution on your measuring stick, right, your ruler, you can have all sorts of different heights. There's like an infinite number of outcomes that vary smoothly. And so, yeah, the distribution for this, you've probably heard of it, is a normal distribution. And that's like that bell curve that you see, which I could draw on my screen, but the bell curve that you see, that's a normal distribution, and that describes many, many things in nature, many naturally occurring things. I've got some more hellos in the chat. Hello, hello, welcome. So, probably you've heard of the normal distribution. Another common example for this is IQ. IQ is normally distributed, which means it's got this curve where you've got very few people right at the bottom end. You've got very low IQ. You've got very few people who are really smart with massive IQ, like Albert Einstein, right? And then in the middle, you've got this kind of like lump, this bell, this kind of chunky bit. And that's where it's most likely, right? And you're most likely to have an IQ around that. And the further you get away, the less likely it is. Now, when we're looking at discrete things like tossing a coin, there's actually some distributions for that. Just like there's a normal distribution for your height or your IQ, there are distributions for tossing a coin or anything where you've got kind of a yes or no answer. So, for example, let's say I was like, okay, I'm going to record all of the days that I catch the bus and all of the days that I miss the bus. So if I catch the bus, it's a success. And if I miss the bus, it's a failure. And that's like a kind of a binary, different, like a binary kind of set of outcomes that we're tracking, success and failure. And you might say, okay, heads is success and tails is failure, or whatever you like, right? You can pick. You might say more than 3 is success and less than 3 is failure if you're rolling a 6-sided dice. And when we model that, the probability of that happening, just like we get a bell curve for heights, we have a Bernoulli distribution. And this is going to record how likely it is for us to get a yes or a no. And this seems kind of pretty simple so far, right? We might say, okay, it's 50% for heads, 50% for tails, fine. But then if we wanted to say, okay, if I toss a coin 20 times, how many times will I get heads? And that suddenly seems a bit harder. And then you get this thing called a binomial distribution. And this is, 20 times of these Bernoulli trials, or n times, right? And we're assuming that they're independent, i.e. so if I rolled a dice or tossed a coin 20 times, the previous ones don't affect the next ones. And they wouldn't really, well, they never would, unless you've got like some kind of intelligent dice. If you programmed a dice on a computer and you rigged it, you could make it dependent, but that would be very weird. So, and then you get this formula here, and this is the probability density function for a binomial distribution. And this might seem familiar to you if you've done any statistics before. This is pretty common, and this is what we call a likelihood. So let's say we wanted to, let's say we were saying, okay, what is the probability of getting 20 heads when we toss a coin 20 times? So K would be 20. We have 20 successes in 20 trials. And so you could sub that into this formula. And then we would get the likelihood, the binomial likelihood of getting 20 heads in 20 trials. And you know as well as me that that's very unlikely for a fair coin. And so we can use this equation to calculate exactly how unlikely, and it would be a really, 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 really small number. Cool. So I hope that's all making sense. You feel like you're learning probability and statistics again. I mean, that is basically what we're doing. This is like a little intro to all of the things that you need to know for this stream that we're doing. So again, like if I'm going too fast, shout out if there's anything you're like, oh yeah, I did this in class. That's great. Hopefully I'm explaining it well if you can recognize it. And if you're completely new to it, let me know if you don't understand it. Yeah, I'm not actually too into the cybersecurity encryption side of things, but I probability is relevant in nearly every field that I've kind of come across. So it's a super useful thing to learn, for sure. Awesome. Okay, so let's say that we had a bit of an idea. Like I said earlier, let's say, okay, we've got this coin. Our friend gave us this coin, and they say, oh yeah, let's toss it, and whoever gets heads, I'll have heads, you'll have tails. And if we land on heads, you get to pick like the movie that we're going to go and see or something, whatever. But you have some reason to suspect that your friend has given you a dodgy coin. It's not biased. No, it is biased. Even. It's not a fair coin. And then what you've got is this prior belief. Prior just means before or like earlier. So you've got this belief before you even flick the coin that maybe it's more likely you're going to get heads, for example. And we can model this using another distribution. This is the beta distribution. And we've got two parameters. And these you can basically think of like, before you toss your coin, you can kind of think of these as like, okay, this is how many, like, this is the ratio of heads to tails that I think will happen. So a uniform one would be 1 to 1. You think it's just as likely to get heads and tails. This is kind of like you're saying it's a fair coin, right? This is like a flat or like uninformative prior-ish, right? You're basically saying, I don't know. This is kind of uniform. If you imagine just a straight line, I think 0 is as likely as 1. Or success is as likely as failure, or heads is as likely as tails. But then we might say, I actually think it's, I think alpha is 10 and beta is 1. That would mean you're thinking, okay, I think it's, for every 1 tail that we get, we're going to get 10 heads. And so you're basically saying, yeah, I really think my mate he's mucking me about here. I don't think this coin is fair. Can we go see the B movie? No, not right now, unfortunately. Unfortunately, we're learning, well, fortunately, in my opinion, we're learning about stats, we're learning about probability. If you wanted to try and apply this to the B movie, I think you'd struggle. I can't think of an application with the B movie. Maybe you had some like prior belief on how many times B's appear and then you're modeling that, but I think that's a bit tenuous. Awesome. Okay. So we're pretty happy, hopefully, that we've got this distribution, the beta distribution, which allows us to say how fair we think our coin is. And really, when we say coin, it's just any binary outcome event, right? Or experiment. And so what we've got is we've got this likelihood, which is basically saying, okay, if I flip a coin and I get 20 heads and I flipped it 20 times, how likely is that? And so we might do that and we might get 20 heads and 20 out of 20 times. And we'll say, oh, the probability of that is going to be really, really low. And so we'll be able to get this number of saying, oh, what just happened was very unlikely if it's fair, right? If it's a fair coin. And then we also have this prior, this idea of like, okay, here's our inclination before we do anything. And we're gonna describe that with a distribution again. So we've got a distribution here. This is our prior distribution. We've got our likelihood. And then we've also got this thing called a posterior. And this is Bayes' theorem in a single line. There you go. And it basically says that posterior, what we think after we've seen all of our data, is proportional to the likelihood, the probability of actually, the experiment that happened and the outcomes that we saw, multiplied by the prior belief. So if we initially thought, it's incredibly unlikely that this coin is biased, we think it's really a very fair coin. And then we tossed it 20 times and we got 20 heads. Our posterior is probably going to say, actually, based on this, the likelihood, that was pretty unlikely to happen. And so our posterior is going to shift a bit. And it's going to maybe, unlike the prior, describe something more like, okay, actually, heads is much more likely than tails. And so we can put this together and we use what's called a beta binomial update. So we've got a beta prior and a binomial likelihood. And this gives us a beta posterior. And this is called conjugacy. It means that we don't have to do any calculus. If we did, it would be hard. And there's some things where you can't even do the calculus. You can't analytically work out what your posterior distribution is. And that's because of this proportionality. You have to start using complicated methods, which we won't go into today. But if you've heard of a Markov chain Monte Carlo, maybe that's familiar to you. It's a very famous methodology. You can use that to calculate posteriors, this output distribution which describes what you really think now after you've seen the data. But what we're going to look at is this conjugate distribution. This is going to be the focus of today, at least for demonstrating what we think. But there are a bunch of different conjugate relationships. So there's not just beta binomial, but there's Poisson normal and so on. There's a whole load of different distributions which pair up nicely, and you can do this update using this rule. This is basically just saying, okay, if we saw 20 heads and we did 20 trials, then our new output distribution will be, okay, let's say it was uniform. We would have 1 and 1 for alpha and beta, and then 20 and 20 and 20 here for the H and the N and then the H again. We would end up with beta 21 and then just 1 here because the N and the H would cancel if they equal. And that would basically be like a very biased distribution. And so we're going to plot some of this and show it, and hopefully you'll understand a little bit better as we do this. And this is called a Bayesian update. And this is how we say, okay, now that I've seen some data, let me update what I think. And again, this is really important I've been to so many hackathons where people use ML models and they don't really think about what they're doing. And actually, just a Bayesian model would be much more accurate for their use case and much more rigorous. So there's some other bits and pieces that we need. I'm actually not going to talk about these till later, but a credible interval, maybe this one is worth mentioning, is that let's say we wanted to estimate the probability of getting ahead on a coin toss. There's going to be some variance to it, right? We're not going to be 100% sure, because how would we know for sure, right? And so the more we flip the coin, the more sure we'll get, right? And how we describe how sure we are is the width of a credible interval. If it's very wide, we're not sure at all. If it's very narrow, we're quite sure. And as we flip the coin more and more times, and we get more and more data, this narrows. And so this is why having lots of data is really important. You've probably heard this, right? If you've got a big data set, you can say things more accurately with more certainty. And so this credible interval allows us to describe that certainty in very concrete terms. Awesome. Okay, so that's great. Now, let's actually do some things. Let's do some coding. And let's see if I can, there we go. Okay, so I'm in VS Code. And as always, you can use, you could use Colab if you want. With most of my projects, this is like very flexible. We're going to be using mostly a notebook today. We might use a Python file if we have time at the end. But for now, we need to set up our environment. And there's a way that I like to do this. You maybe don't do this yourself very often, but I like to call it stats, but then the actual virtual environment folder I'd soon have called .vnv. And this is very common that you have it called this, but it just means that when we're typing on our terminal, it will say stats instead of .vnv, which means, oh yeah, we know what virtual environment we're using. If you've got multiple projects on the go at once, it can get a bit confusing sometimes. So this is good. So then if we want to activate this, this will probably vary depending on the terminal and also the operating system that you're using. This is what works for me. You might have like a slight variation on this. And so now that I've activated my virtual environment, you can see it's here, stats, great, that's what we called it, perfect. And that's just corresponding to this here. Now at the moment, it's empty, we've got nothing installed. I'm going to do that next. See, there's some chatter. I feel like, are you saying you've got some interest in probability? I hope you do, I mean, you're in the right place if you do. Probability is the best. Machine learning is an extension of probability and stats. In many ways, yes. There are kind of more like black box models, the kind of deep learning neural network stuff it's still, right? It's still calculus, linear algebra, and statistics to some extent. And you can definitely use a lot of probability with it, but yeah, in general, machine learning is very much, probability and stats, you can't really take them and separate them from machine learning. So this is super useful to know. Okay. Yes, I can expand on this distinction for you. So a confidence interval and a credible interval are different. And the difference is we use the term confidence interval in the frequentist paradigm and credible interval in the Bayesian paradigm. Now let me explain what that means. The Bayesian paradigm is what we just described, where we have this subjective idea, a prior belief on what we think to be true. So we might think that the coin is biased, or probably more realistically, for example, we might have some expectation on how prevalent a disease is, right? This is a prior belief. We think, okay, no one really has this disease. And then we can use that in our modeling to calculate the likelihood of someone having the disease, given they've tested positive on a COVID test, for example. And so we can use Bayesian statistics to do really meaningful things like that. In frequentist statistics, you don't have any of this kind of subjective probability. You have no way to express a belief that you may have. And so you can't use existing research or expert information. Let's say you had an expert who you were consulting with and they said, oh yeah, like as far as we understand it, bees like lavender plants more than, I don't know, marigold flowers, right? Then you couldn't use that in the frequentist paradigm, not very easily. Whereas you could in a Bayesian paradigm, you could when you're doing your experiment and your modeling. So that's the difference between Bayesian and frequentist stats, right? These are the kind of two different ways of thinking about statistics. And in frequentist stats, you have a confidence interval, which kind of expresses the range that you think your parameter is in, or maybe a prediction. It doesn't describe a probability. So you can't say, okay, this is a 95% confidence interval for theta, and therefore there's a 95% probability that theta is in this range. You cannot say that in frequentist. So with a confidence interval, it is not a probability statement. What it's saying is that in 95% of your experiments in your different, like, if you ran it 100 times, in 95 of them, it would be in this range. And that is distinct, that is different, because the interpretation is slightly different. In Bayesian stats, you have credible intervals, and that is a direct probability statement, which is good. It's more interpretable in my opinion, right? It means you can say, okay, I do, like theta is 95% with 95% probability in this range. And so it might just sound like a bit of a semantical difference, a difference in the way that you phrase it, but it really is actually quite significant because it affects maybe the decision that you make after that as well. Did I hear B? No. No Bs. There are no Bs here. I'm sorry. That was very clear. I'm glad. Yeah, I mean, I really recommend reading more about this. There's some great guides online. I'll try and link some at the end. I've got some resources saved. It's a super interesting and useful area to learn about. Cool. So, getting back to our little project. Right, we're going to do some experimentation, but first we need to install some stuff. So we're going to pip install, and then we want PyMC, and we want it to be this version specifically, and then we want Biz Streamlit, which probably most of you are familiar with, Pandas, which probably most of you are familiar with, and NumPy, and then we'll make it quiet as well. And so while that installs, let me just talk about these very quickly. So PyMC is something that provides a Bayesian engine. So if you're trying to do more complicated stuff like microchain Monte Carlo, or your more advanced Bayesian modeling, this is useful. I don't actually think we're going to use it that much, but I think installing it just in case is probably good. Others is useful for handling plotting as well. So when we want to think about the distribution that our posterior has, this saves us some time. I'm actually not massively familiar with these two because I normally do this kind of statistical work in R. I figured most people are more comfortable with Python, so we'll use these. But what I would recommend is if you're interested in learning this further, learn a bit of R. It's a great language for statistics, and the packages, at least in my opinion, are much more intuitive and comprehensive. So I do recommend that. And then Streamlit, of course, allows us to build nice and quick UI and visualizations. And Pandas and NumPy allow us to manipulate data. So that's great. Right. Now, what we need is some data. And I've unhelpfully closed the notes which have the data in. So let me pull up my notes, and then I will send a URL to the data. We're going to be using, just to begin with, the Titanic data set. You've probably heard of it or used it a bit. Yeah, there you go. There you go. Saves us from having our terminal full of nonsense. Yeah, R is so great. Really recommend. So yeah, the data that we're going to be using, Titanic, this is just like a convenient GitHub link that I found. And so I'm going to download it now. You can do it your own way. I'm literally just going to that URL and clicking download, and then I'm pulling it in here. Cool. So we've got our data, and I'll give everyone a second to catch up if they need to. This is like a classic data set, and what it does is it's got all of the information on different passengers and basically whether they survived the Titanic catastrophe or not. And it's super interesting to look at for many different reasons, but you'll notice that survived or did not survive is a binary choice, right? Just like tossing our coin or saying, okay, is this dice going to roll more than 3 or less than 3, right? We've got this, one or the other, 2 outcomes, a binary outcome. And that means it's going to be nice and easy for us to do using our distributions and the little discussion that we've had around discrete data. So hopefully that's going to be really nice and straightforward. So let's call this like experimentation, and we're going to make a notebook, and it's going to be upset with me to begin with because I haven't installed IPyKernel. So let's try and run this. We're going to click our virtual environment. You can also do that here. And if we run this, it's going to have a tantrum. Yep. There we go. And it says it wants IPyKernel, and we're going to just install that. You can also just pip install it, but I always forget. So we'll let it do that. And then while it's doing that, we're going to load in our data. Again, if you're familiar with pandas, this is going to be pretty comfortable for you, hopefully. And it's called Titanic.csv. If you've named it something else or downloaded it in a different way, make sure to adjust. And then let's just see what we're looking at. I mean, we've already had a little sneak peek here, but let's pretend we didn't. We'll have to wait for this to finish installing first. So we'll give it a minute. Now is a great time for questions. If you've got any questions. Questions are always welcome. I use pip. Have I typoed? Yeah, I use pip. I'm afraid I'm probably not the best person to ask on that kind of decision. Pip is yeah, my preference. It's just what I've always used, to be honest. I did use like Conda for a while. I like Conda and the way they like handle lots of things for you. Hello? Right. Someone spot the obvious mistake that I've made. Oh, okay. Right. Pro tip: do not typo. So I ran a Type Racer mini event yesterday, which was super fun. And I thought I would be better now. I thought I was going to be good at this because I always typo in my streams. This is, if you've been to a few of my streams before, this is like an infamous Quinn moment. But alas, clearly it's not done that much. Okay, great. Conda scares me. Never works. Yeah. I mean, Conda's good in like some ways if you're using kind of the same set of packages all the time. So once you've got your virtual environment set up, you can use it in many different projects. But if you're like doing lots of different things, I don't know. I think Conda is nice in that it like abstracts some of the mess away, where sometimes with pip you have to deal with more kind of like conflicts and things. Do I do any advanced visualizations? Not all that commonly. I'm a big fan of like simple visualizations can convey very advanced things. So even if you've got like an advanced inference or point that you want to make, simple, like bar charts and so on are really great. I think there's some people doing some stuff on some visualizations. I think maybe UT is doing some sort of visualization this week. So that's maybe a stream to check out. But yeah, I mean, like we're going to be using mostly Matplotlib. Actually, maybe not. Maybe not, actually. I don't know. We'll see. Maybe we'll change it up. But yeah, so hopefully everyone has reached this point as well. We've successfully run this and we can see our data. We've got all of our passengers, they've got IDs, that's great. We've got whether they survived or not. So 1 is survived, 0 is not. We've got some details, their sex, their age, whatever these are, I don't really know, don't really care. How much they paid, right, this could be interesting. Great, okay, so we've got our data loaded. This is a good first step. And so hopefully by this point, you've got a notebook set up, you've got a virtual environment, and you've got all of your things installed, and you've got a data set in your working directory or equivalent. It's loaded somehow. And we're going to be working on this idea that we use evidence to update our beliefs, right? This is kind of the foundation at this point in the workshop where we all need to be at. If there's any of that which doesn't make sense to you, tell me now. Otherwise, we will get going with a little bit more. Any questions? Oh, your day job is doing advanced visualizations? That is very cool. Yeah, I don't do a ton of that. But I've done a little bit. I mean, R I think is great for this kind of thing. ggplot. Love ggplot. So good. Cool. Okay. Awesome stuff. So let's first do a quick experiment. So let's do some imports. So these will be our imports, and let's import random. This is going to be pretty useful because we're going to be simulating some coin flips just before we get onto the Titanic data. Again, I'm just doing like some pretty. I think we did install Matplotlib, didn't we? Yeah. Okay. Yeah. We're going to be using Matplotlib for now, and then maybe we can do some more exciting visualizations later if time permits. But we will see. Oh, not that. Okay, right. So I'm just importing some packages, and then let's simulate a small data set. So and we're going to say, okay, the number of flips. So we're going to be pretending that we've got, you know, a little digital coin, and let's do 10 flips. So this is pretty small, and we will say a random dot choice. Oh, actually, let's make this a list. Let's get that the right way around. There we go. Okay, so we're making a list, and we'll say random dot choice, and then we'll do heads or tails, and yeah, perfect. Okay, so Copilot's helped me out there and just predicted that last bit. So what this is going to do is it's going to randomly pick H for heads or T for tails, and it's going to do that however many times we've specified here. This is our little data set, if you like, and let's count all of the heads. So we'll do flips.count, and then tails we could also count, but given that it's binary, we know how many heads we've got, we can also just do the number of flips minus heads. So we're beating Copilot there on being efficient. Okay, and then the next thing we're going to do is going to say, yeah, let's give ourselves a prior. And look at this. This is crazy. This is very impressive. Copilot really knows what we're doing. And let's say that we've got an alpha prior and our beta prior. So this is like the number of times, you know, the ratio almost between our heads and tails. They're kind of like, okay, do we think we'll get 10 heads for every one tail or not? Like, where's the balance going to be? What's the ratio? And let's just assume that it's a fair coin. And we can play around with this in a bit. But then what we're going to do is we're going to do what's called the conjugate updates. Okay, and that's what we discussed, right? This is where we say, okay, we want to get our posterior alpha, which is, again, we're using the beta distribution with a binomial likelihood. This is just when we have either a success or a failure for each turn or each, you know, yeah, I guess turn is good if you flipped a coin each turn. And we can update this using a rule, and the rule is that for the alpha parameter, we take our prior. So for the alpha posterior, we take our prior, and then we just add the number of successes or heads in this case. And or, you know, k if we see, you know, k successes in n flips, right? So heads here is a count. Hopefully that's kind of making sense a little bit. And then we've also got our beta, and it's much the same. Tails, remember, is just the number of flips minus heads. Now you might remember that we spoke about n minus k when we're going through the conjugate update, the Bayesian update that we were talking about earlier. So you could put that in here, but tails is just the same thing, so we can use tails. And so you can kind of see that actually, okay, beta is representing the number of tails that we get, and alpha is representing the number of heads. And we're going to update it using the data that we've seen. So we had this prior belief, this thing that we thought was true, right? And we thought, okay, it's a fair coin. We think we're going to get the same number of heads as tails. And then we've seen how many heads we actually get and how many tails we actually get, and we're updating it. And then we can also then, let's say, draw some samples, right? So if we wanted to produce that credible interval that we were talking about, we need to know, okay, like how much of the time do we actually, like these results remain true? And, you know, we can do this by like simulating the data that we've got. This is kind of like bootstrapping, if you've heard of bootstrapping. But what we're going to do is we're going to just draw up some samples. So we're going to draw posterior samples. And what that basically looks like, we'll say, maybe I'll type it out and then talk it through. It's probably simpler. Got random beta. So this is our distribution. And then we're putting in our parameters, right? So remember that alpha and beta are parameters in our distribution. So these help define the shape of the curve, like that bell curve, but this is actually slightly different because it's beta. Okay, and then we will say size, and let's just make it like big, 5,000. Perfect. So this is gonna resample a bunch of times. And using this, we can compute this range that we kind of say, oh yeah, across all of these different samples that we've made, this is actually where our values fell. Cool, we got a quick question. Okay, so someone joined a bit late and wants to know what the prior values stand for. Yeah, okay, so we've discussed a little bit about Bayesian statistics. So if you're familiar with Bayesian statistics, hopefully you'll be able to pick right up. But if not, for anyone who's just joined, The premise is that, unlike frequency statistics or classical statistics, you might be more familiar with these. The way that Bayesian statistics works is that you have this subjective component to it, subjective probability, where you can say, okay, I have something which I think to be true, some like idea, and before seeing the data, I can describe roughly what I think will happen. And so this might be like, okay, you might be asking an expert how different stocks will perform. You might have like a stockbroker or even some professor, right, in economics, and you might be saying, okay, how will the market perform if we do this or whatever, right? And you produce this distribution, and the distribution just describes the probability associated with each outcome. All of the things that can happen, how likely do I think each one is? And this is helpful because it's a way that we can describe what we think to be true, some idea that we have, some information even, in a statistical and rigorous way. And so our priors here are parameters of a beta distribution, which basically each of these parameters represents for a binary set of outcomes, how likely we think each one is. So if we had 10 and 1, it would mean that we think, if you think about this, when I say binary in terms of successes and failures, so let's say we want heads to come up and we flip a coin. For every one tail that we get, we think there'll be 10 heads. And you could also just flip it. So you could say, okay, we want tails to happen. And in the same way, you might be like, okay, so we'll have one tail for every 10 heads. And so you can play around with this and define it how you like. But the premise is that this is almost like kind of pseudo, like the ratio that you expect to see is like a kind of a pseudo count. Yeah, I'm glad that makes sense. That's cool. So yeah, and basically what we're doing with Bayesian statistics is we're saying, now that we've got our belief, we've got some data, we can update our belief with the data and produce a new belief, which is evidence kind of grounded. And this is really important. It's really useful. It's the foundation of awesome machine learning. We love it. So this is good. We're drawing some posterior samples, and now we want to get some credible intervals. And we can do that by saying, okay, we've got a credible interval lower, and this is going to be pretty straightforward. It's just a percentile, right? And so let's do a 95% credible interval. This means with 95% probability, we believe it's in this range. You can also do this using the formula for the distribution. So we're using sampling. Basically what we're saying is, okay, we've got this equation, this distribution, and we're just gonna like ask it to spit out a whole load of numbers that fit on this curve, right? So what we're doing is saying, just give us a number that's on the curve. And it gives us loads of numbers that are on the curve. And we're basically working out, okay, now that we've got all of these numbers, like where are the percentiles? And then we can work out a range from that. You can also just do that from the equation for the curve, which obviously we have. Sometimes you can't do that, and so sampling is a good solution, but in this case we could. But I think this helps with the intuition, realizing that actually a credible interval is saying, okay, the probability that it falls in this interval is very clearly the case, because what we've done is we've just done it a whole load of times, and then we've literally just produced, okay, 95% of them are in this interval, where we can see all of the data and say it is in this interval. So this is a really neat way of getting that intuition. Hopefully that makes sense. Again, I think once we do some plots, it will become clearer. And so this is a 95% interval because 2.5 plus 95 is 97.5. Cool. Okay. And we might also want the mean. So let's get the posterior mean. And that's the mean. There we go. Perfect. And this will be, yeah, like the most likely value if you like. Cool. Okay, let's do some plots. This is where everything goes wrong, because plots are stressful. I feel like I always have bad luck with plots, and it's just like, oh, the formatting goes to pieces. But we'll see. Let's see if we can get this right. So what we're doing right now is we're setting up our axes, and we're doing that according to our parameters and the data that we've seen, and the curves. So this is the PDF. Now, you might be like, oh, what's a PDF, Quinn? Well, actually, we've already mentioned this. This is just that curve, right? The curve which says, okay, for this bit, this is how likely it is, right? If you imagine the curve, this is, at the top, it's most likely, and so on. It stands for probability density function, which basically just says, at each point, like, how likely is that to happen? And let's finish this off. Great. So we've got... X. Ha 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 ha. There we go. That's better, isn't it? I was like, what have we done here? Okay, perfect. Perfect. So basically what we're doing is we're saying, yeah, for each of these values, let's plot the likelihood, the probability of that occurring. Cool. Okay, so we've produced our axes, I guess. Let's make the figure. This isn't really an introduction to matplotlib, so hopefully you kind of have a vague idea of how matplotlib works, but if not, I think it's pretty intuitive. We're setting the size there, and then we can actually do the plotting. So we'll say, right, we've got our X, we've got our Y values, and then let's set a label. Sure, let's set a label, and we will maybe use an F string here. Let's say we've got a beta distribution, which actually has, so this is how you commonly write a distribution. You might have like 3 and 1, right? This would be our alpha and our beta, or beta. But in this case, we don't know what they are yet, but we've got the variables, so let's put them in. We love F strings are good, and then we'll just say this is actually the posterior in case it's unclear, because it could also be the prior, right? And they have the same form. And then we'll say, let's fill between. Do we have a typo? Oh yeah, perfect. Thank you. Yes, very true. Thank you for pointing that out. Yeah, I would have run it and been like, oh no, why is my code broken? Yeah. And I really thought my typos were going to get better from now on. But alas, does not seem to be the case. Okay, let's get this right. Okay, we'll format this. Right. So this is just a whole bit of visualization stuff. Like I mentioned earlier, it's actually not my favorite thing to do, playing around with visualizations. I do love a pretty graph, you know, but I frequently get frustrated by them. Maybe someone else should do a stream on how to be a pro at visualization, because I'm constantly running into problems. I can never get everything to line up the way that I want, the scales and so on. But you know, right? Okay, so this is our credible interval, and we're using the bounds, basically the lower and upper bounds that we defined earlier. We're filling between them. Cool. Okay, and then we want, yes. See, Copilot knows, which is kind of scary. And then we'll give it a dotted line, a dashed line. We'll say the line width is 1.5. Maybe we need a label as well. So this is for the posterior mean. And let's again use an F string, and we'll say posterior mean equals, and then yeah, great. And we're just rounding it. Copilot's done that nicely for us. Cool. Okay, that's done. Great. What's next? Well, let's add a label to our x-axis. Yeah, sure. I mean, it's probably better to say the possible probability of that's, because it's not definitely true. It's not the ground truth, right? Maybe it's good to be super clear with our labels here. And then this is the density. Let's get some quotes in there. Perfect. And then we want a title. So posterior distribution of point flip probability. Yeah. It's true. Maybe we want I'm kind of inclined to say let's use another F string and actually put the number of heads that we get. Yeah, I think that's maybe more useful. We could use the number of flips instead of tails, but I think that's fine, because this is going to be helpful for us. Right, and then let's just these are some layout adjustments. This is the moment of truth. We typed out a lot of code. We probably should have done this bit by bit. But okay, awesome. Oh, I'm so happy. Look at this. Happy days. Okay, so you can see that we tossed our coin 10 times, and it was completely random, right? Equal likelihood. and we got 7 heads and 3 tails. Interesting. So this is our posterior. This is the curve that I was talking about, and this is our mean. You can notice it's actually not at the top. That would be our mode. This is the mean, and this is our credible interval. So we're basically saying, okay, with a 95% probability, it's between, like, I don't know, 0.4 and 0.9-ish, which is actually quite a big range. That's 0.4 in range. You're like, okay, well, this is not very good, right? This is like really big, and actually we know, because it's completely random. We didn't tell the model this, but we know that it is completely random, right? We know that it is just as likely to get heads or tails. Actually, we kind of did tell the model this, right? We gave it the prior. So even though we gave it a prior, uniform prior, it's actually done this kind of curve. Like, okay, fine. We could change this to be 2-2, and that would be more informative. What we're basically saying, we've got a beta 2-2 prior. What this is basically saying is, like, it's not uniform, but it's got a bit of a curve to it. But let's stick with this for now, and let's say, okay, well, let's increase it to 15. Okay, well, this was much more normal, right? We got 7 and 8, and actually, I mean, I say normal, but it's more normally distributed as well. This is kind of like looking a bit more like a bell curve, right? We've got an 8-9 posterior, so that's like nearly as likely. We're saying tails are maybe slightly more likely. Our mean is 0.47. This is much closer to 0.5, but actually the range is still massive, right? Like, okay, we know that this is more accurate, this is more correct, but the certainty hasn't gone down that much, even though we increased it by 5. This is maybe, what, 0.23 up to 0.7-ish. So that's still nearly 0.5 in range, right? Which is pretty big. So, well, let's try increasing that like a lot. Let's run 100 times. Okay. Now, not only is it fairly accurate, 0.47, it's just as accurate actually as when we did 15. That's not great, but it's more accurate than the first one that we ran. But actually, the most interesting thing is we can be more certain. So if we didn't know that this was actually a uniform, an equally likely a fair coin toss, we could say, okay, it's between just under 0.4 and 0.6. So that's only 0.2 in range. Now let's increase it again. Let's make it like bigger, like really big. It's going to be too big. Nope. Okay, 0.3 seconds. I mean, that's so fast, isn't it? And so we've made this massive, and we still got more tails than heads. Interesting, but our posterior mean is 0.5. It's tended towards this exact, like, perfect split, and that's really cool. We've got some thoughts in the chat. Stay away from the top of the bell curve. They mean that. Nice. Yep. Got some humor going on. But yeah, so we can see not only is this more accurate, right, but actually the credible interval is, I mean, it's like tiny. Can I zoom in? Can't zoom in. Okay. I probably could if I tried, but yeah, I mean, it's like really small, really small. It's basically extremely unlikely it's anything else, right? And this is cool. What we've done is we've said, okay, now that we've got more data, we can make a statement about how certain we are. And so when we're making decisions, whether it's a decision in the way that we build our project, right? Maybe decision making in the structure or architecture or the problem that we're trying to solve, this can get quite meta. But actually, even in the solutions that we're providing through our projects themselves, you can use this to help inform the outcomes, the decisions that you make. Let's say you've got a whole bunch of different actions and you think they might affect things in different ways. You can use this to inform that, and we'll actually do that in a bit. Cool. So the reason this tightens this confidence interval, or credible interval, sorry, not a confidence interval, although a confidence interval would also tighten in this situation, is because we've increased n. We've increased the number of flips, and this means that the variance has shrunk. And this is to do with the nature of the distribution that we're using. This is kind of like it's kind of like the law of large numbers, if you're familiar with that. It's kind of like a Bayesian equivalent. There is like an asymptotic limit for this. Asymptotic just means that as n tends to infinity, like this is going to shrink to 0 maybe, or it will shrink to something, but in this case it would shrink to 0. And you can kind of see that, right? Like it seems to make sense. But there's a theorem that describes this, but we won't go into it. That's going to get quite theoretical. So we're hopefully pretty happy with this now. Yeah, if there are any questions, now is the time. I've left my water at the other side of my desk, so I'm going to just swivel over here and grab my water. There we go, my water bottle. Remember to drink. and have snacks and things when you're hacking. Keep yourself well fueled, keep your mind well resourced. And we'll take a breather, because I feel like we've gone over a lot of theory, a lot of thoughts. Hopefully we're kind of vaguely happy with this idea. If there are questions or even just ideas or thoughts, let me know in the chat. Maybe give me an emoji that describes how you're feeling about this content so far. If you're like, oh yeah, this is super easy, give me like a smiling, laughing face. If this is like, oh, this is scary and sad and hard, give me like a sad face. If you're like, oh yeah, this is okay, give me like I don't know, like a sunglasses emoji or something. we got some. Okay, this is good. We've got some good results. People are happy. Perfect. Awesome. Right. Well, I think in that case we can maybe keep going. Awesome. The posterior mean again. Yes. So this is basically just. Let's see what the easiest bit to use to explain this is. So if we've got this this kind of like data generating function, right, which basically says, okay, we've got a probability associated with. Let me actually rerun this with like just 10. So our prior, actually our posterior. Let's use the posterior because this is what we're doing to generate samples. So when we're generating these samples, let's start with that. We're generating these samples using this curve. And this curve is kind of just like any other function. The difference is that it integrates to 1, which means that we've got like a probability associated with all of these different things. Because it's continuous, not discrete, you can't say, okay, what is the probability of any individual bit, but you can say the probability of a range. And what we've done is we've used this function. We've said, okay, let's pick a number that is on this curve. And so what we do is we instead of using the actual equation, we've just used this like special mysterious simulation sampling algorithm, which is helpfully done for us using NumPy. You can actually write these yourself. They're a little bit beyond the scope of this 2-hour slot, but they're pretty cool. Again, I can link to some resources if people are interested. And so what we're doing is we're simulating. Imagine we get like a data point every time that we prompt this, we get a data point. So we've got 5,000 data points. So that, imagine like this, one here, one here, one here, one here, one here, all going up the curve, right? All going up the curve. And what we've done to get the credible interval as well as the mean is we basically just said, okay, now we've got a bunch of data. Let's just get like the 95% interval where 95% of the data sits. So let's order it up and then just pick the percentiles. Imagine just drawing a line. Okay, 2.5% is lower here, and then drawing a line up here is like 2.5% is higher. In between those, we've got, well, 100% minus 2.5 minus 2.5. We've got 95%. Great. So that's our 95% credible interval. But actually, we've just worked out the mean in the same way. We've got these 5,000 data points. We've got all the way up here, and it's just got us a value, right? And so we've plotted it. And you might be thinking, well, why is it not going through the top of this curve? Well, like I mentioned earlier, this is the mode, but the reason is because this is not symmetrical. Unlike a normal distribution, which is a perfect bell curve, this is not symmetrical, and that's kind of okay. If it was symmetrical, this would go through the middle, and the mean and the mode would be the same, but it's not. And so if we let's run it like, okay, yeah, here we go. So this is even more asymmetrical. We could run it. Hopefully, if we run it, okay, yeah, this is even more asymmetrical, right? We've got one head and 4 tails. So you can see that 0.5 is actually still in our confidence in our credible interval, and that's like, okay, good, yay. We'd hope so, right? But it's kind of towards this end of it, right? And we can see that the mean is not falling through here. This is because it's skewed, right? So we've got more of the curve is this side. So 50% of the density is this side, and 50% of the density is this side. And that's what the mean means, basically. That it's kind of like 50% of the density is on either side of it. Got some more emojis in the chat. I'm glad to see that. We've got a sunglasses cat. That's awesome. I've never seen that emoji before. I can't even see what this is. Can someone help me out here? It's too small on my screen. It looks like a tap. Is it a tap with water? Maybe it's a tap with water. Is this a reference to me hydrating? Hydration is good. I do recommend. Oh, stats is so good. Stats is so good. I will at the end link some cool some cool stats resources that can kind of help with this stuff. But yeah, auto for clean data. Yeah. Oh yeah, that's true. That's what we're doing, producing the perfectly cleaned models. No flaws at all. No, there will be some flaws, but that's okay because we have a statement around how confident we are or how certain we are, right? Cool. So we've built this little coin flipping machine. That's pretty cool. Let's say we want to. Okay, let's say we've done this, but we're not really like investigating it at each stage. Let's say we wanted to like flip a coin a few times and then investigate what our posterior looked like, and then flip it a bit more and just keep going. So let's write some functions to do that. We've already got NumPy installed, imported even. Let's import time sys. We've got random, right? We got random, yeah, okay. And then let's say we've got some true p-value. And so this is the probability of heads, and let's not make it uniform. Let's not make it fair. Let's say 0.7. And then maybe we'll set a seed. Would be good if I could type. We'll do 42, sure. Okay, and then let's say make a function, and we'll call it stream flips, because we kind of want to make this like, you know, like a stream of coin. I mean, Copilot already knows, but like a stream of coin flips, which is a little bit more continuous. And we'll say 25 for now, and we're going to add a delay, and this is going to allow us to think at each stage. So what we've said is we've said a true p-value, but in reality we wouldn't know this. And so what I might do in a minute is hide it and change it, and then you can all guess what you think it is, and then we'll realize very quickly how important having a rigorous framework is for dealing with this kind of thing. So what we're saying is basically, okay, if we get a random number and it's less than our true value of p, then we'll get a head, and otherwise we get a tail. This is basically just saying pick a tail with probability 1 minus p, or pick a head with probability p. And then let's print what happens at each stage. So yeah, this is good. And then we will do time.sleep, and then we'll do it for the delay. Okay, and then so like if we run this now, and then we'll just run it with the default settings. Okay, we get head, we get a tail, we get a tail. Okay, head, pretty even so far. Head again, 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 head again. Now this is like, oh, this is kind of getting weird now. If this was a fair coin, we're going to be pretty sure that this is like weird, right? If we thought this was a fair coin, we're having doubts. And look, I mean, this is insane. We got 2 tails in the whole thing. Even that is unlikely. I mean, we probably should have expected to get, well, at least 7 tails according to this true probability. So this is really, really strong. Now, what I'm going to do is, I normally have like a second screen streaming. I can just move things across and hide things, but I can't. Let me think about how I can do this. If I just, if I move the whole window, get the window to move. Oh no, it just stays. Okay. Okay, here's what I do. Right. Okay, I'm now setting a new p-value, and I want you all to guess. Okay. Perfect. Okay, let me add it back. Right. I set a new p-value, and okay, we have some more questions in the chat. Before I run this, we'll answer these. Why isn't the credible interval 97.5%? So we had 2.5% on the lower tail, right, the lower end, and we had 2.5% on the upper end. So 2.5 plus 2.5 is 5, and so the bit in between, the bottom bit and the top bit, is 95, right? Because we've got 2.5 plus 95 plus 2.5 gives us 100. So I can see why you'd think it's 97.5, because you're like, oh, it's 2.5, but actually it's 2 lots of 2.5. We've got both ends, the top and the bottom end. So that's why. Oh, sorry, I should have read the whole thing before replying. Yeah, you spotted it before I even said it. Well done. Yep, this coin wasn't fair at all, was it? I mean, If our friend gave us this coin, we'd be like, you know, you're a bad friend. You're rigging this coin flip. Yeah, so, but now I've changed the true p-value. And what I'm going to do is I'm going to run this, and I want people to guess. Try and guess the probability of getting ahead. And we'll see who gets closest. So I want some guesses in chat. You can guess as it goes along, and then you can update your guesses as it goes. Let's give it slightly more delay. Let's do it for 20, but then we'll do a delay of 1.5, right? And let's run this. So we've got a tail first, and then a tail again. Now I'm starting to think, this is a lot of tails. Oh, this is a lot of tails. So any guesses in the chat? Okay, we've got a head. Okay, so far we had 10 flips and we had 2 heads. So you might be thinking, okay, maybe the probability of a head is 0.2. We've got a lot more tails. Maybe we're thinking the probability of a head is now a bit lower. I don't know. It's kind of hard to do, isn't it? Hard to guess. So we got 3 heads. Okay, true. So we got some thoughts here. The true p-value is 0.3. We got 3 heads, but it was in 20 flips. So my guess on this would be probably most likely value would be 1.5. Half that, because we got 3 and 20, which would be the same as 1.5 and 10. Should we check? Any other guesses? Any other guesses? So far, 0.3 is our guess. Okay, let's guess as a team that it is 0.3, and it was 0.1, so even lower. So yeah, I mean, we got slightly more heads than we'd expect. Interesting, isn't it? Maybe we'll do that once more. This is fun. Let's do it once more. I'm gonna update it once more, and then we'll see. Let's add it back and let's run it again. And put your guesses in now. Okay, we got a tail, we got a head, we got a head. Now I'm thinking, okay, there's way more heads. It's got to be heads, right? Oh my gosh. So let's see, we got 1, 2, 3 tails in 10. So maybe we're saying probability of heads is 0.7. Interesting, we're getting more tails now though. Any guesses? Any guesses what the probability of heads is? It seems the heads are a bit more common. Should we count them up? We got 1, 2, 3, 4, 5, 6, 7, 8 tails. So half that, 4 in 10 tails. So we might say, okay, maybe 0.6. And 0.6 is the most likely estimate, right? The maximum likelihood estimate. And you can work this out. What we've done is we've just counted it up and then done it as a proportion, and that actually turns out to be true. This is something you can show using all the different formulas and equations. You can derive that result. But we've got some guesses: 0.5, 0.65. Actually, the answer was 0.5. So a great guess from Amari. 404 not found. You didn't quite find the right answer. Answer not found. Answer 404 not found. Yeah, unlucky, but close, very close. But yeah, 0.5 was correct. So what we're doing is we're trying to guess this by ourselves, and it's not very good. And you know, like, if we were to like build an ML model to like try and guess this probability based on this, like we could do this and we would end up getting the same results as our Bayesian model, but that would be computationally expensive. It would be a little bit more challenging to get actually a degree of certainty. We wouldn't know how certain we are. Getting this credible interval is a little bit harder. We've got some thoughts that maybe actually stats here is better than machine learning, at least classical stats for this situation is perfect. It's perfectly sufficient. And so let's build something that's is a little bit more intelligent and allows us to see it each time what our posterior is. So we're going to import others. And like I said, I'm not actually massively familiar with these libraries. I normally use R, where lots of these kind of things are a little bit more built in. But we're going to be doing some plotting, and we're going to make a function again. And this is going to be, we'll just call it base coin, and we'll say we've got flips, and this is going to be the history, the number of flips that we've had to date. So we'd give it all of this data, right? And it's going to update using that kind of conjugate update that we said. So we'll start with our priors, and again, let's just set the defaults to be a uniform prior, a flat prior. We think it's a fair coin basically, and then we'll say with pm.model as model, and we'll say p is equal to So we're getting out our posterior. Oh, that was a lot of prediction all at once. I only wanted that line. Okay, let's see what else it did. So, observation is binomial. That's true. So this is our likelihood. And then, observed is equal to count h. Sure, this is okay. This is okay. This isn't how I was going to do it, but I think this will work. So good job, Copilot. So what it's doing is it's basically saying we've got n flips, and this is our kind of like probability that we're thinking it is, and using our prior actually. Sorry, I said this is posterior. This is actually our prior. And then we are saying, okay, the number of heads that we see is literally just the ones that we're observing. And this is true, right? We could also set this to be 1, and then we could have our observed as a list, and that would be, yeah. Let's do this. I think this is slightly nicer. So instead, we will do, and I'm doing this in part because I know this will work. I'm a little bit hesitant to use Copilot's code without being 100% sure, but you know, you could, if you wanted to, use that code that Copilot just drew up and just run it, and I think it would probably be okay. But what we're doing here is we're making a list, and we're saying, okay, for every head that we see, we'll count it once, and otherwise it will just be a 0. And that's fine, right? And then we will get a nice sample out, and this again, like, I'm not going to go into too much detail here because this is probably kind of like overkill, to be honest. Like, we probably don't need to do it this way, but what we're basically doing is we're producing a posterior, and we will say that we don't want a progress bar. So this is just like some parameters. What I would recommend is looking up the PyMC package. But like, again, the focus on this is much more on the intuition. So we're gonna kind of skip over some of the, yeah, we used 42, we used 42 before. We'll skip over some of the kind of like more technical details of the actual what am I saying? The actual functions and things themselves. But we will talk about the intuition behind them once we run it. So don't worry if this is like, why is this so confusing? But it's basically just a whole load of probably fairly new syntax that you are not like massively familiar with. And we're going to be using a HDI, which is a highest density interval, which is kind of like a credible interval. What it is the credible interval with the most stuff in it. And obviously, if you centered your credible interval on your mean, you would get that anyway. So that's kind of good. That's kind of good. It's kind of basically what we've been doing. It's just a slightly different way of thinking about it. But yeah, what we're getting is like, okay, where's the most likely, you know, the narrowest interval, which is just all of the most likely bits in. Let's again do what we did earlier and use an F string, and we will say heads. Oh, yeah, this is perfect. Copilot's just producing the same thing, and that will do. That will do. Are we printing the? Let's put in a colon here and actually put in our posterior distribution, and it's completely getting this wrong, but it will be beta, and then and then alpha beta, which are our parameters. I'm happy with this. Nope, no, I'm not. No, I'm not. This is our prior. You'll be like, oh, we haven't updated these. No, we haven't updated these. This is our prior still. The update is happening kind of implicitly in this function, so let's do it ourselves. Again, we're using conjugacy, which just basically allows us to keep track of the count overall and just add it on. So it's nice and simple. And then we will just show it. We won't bother with the labels for now. This is going to be a slightly scuffed chart, but that's okay. I'm feeling like this is going to be okay. Yeah, I'm not. Okay, it's just doing setup stuff. It's fine. Yeah, I think this is going to work fine. I'm just checking my notes. It seems good. This seems good. This seems okay. This seems fine. Ah, I typoed. I typoed. Oh yeah, thank you. Perfect. Okay, right. Okay, good. So now we need to update our flip function so that we can interrupt it and plot the posterior whenever we like. So we'll write a new one. Actually, it's probably easier just writing a new one from scratch. Flips, and then we'll call it Bayes. And so this is going to demonstrate how actually using this posterior and these calculations is going to be advantageous to us because we will be able to make more informed decisions. Beta equals 1. And then we'll say flips. Yeah, that's fine. And then we'll say, okay, for I in range, and then we want 1 and plus 1. And then we'll say, yeah, flip is equal to, okay, yeah, got this. So we've got the same kind of like code that's going on here. And then we will add the flip to the flips. And then we can print. Yeah, okay, fine. And then we'll say time.sleep. So this is all basically as before, but then what I want to do is, instead of running our function every time, actually no, let's run it every time. I think that's fine. Okay, cool. And now, hopefully we run this. This might take ages actually to run every time. Ah, wait, do I still have a typo in? Or did I just not rerun it? Maybe I just didn't rerun it. We can hope. Okay. So how is it? We've got 4 heads. No, 4 tails even. Okay, so this is not updating. That's fine. But the plot is okay. Let's go back and fix that error so it's a bit clearer. So this is the title, and we're actually not tracking this properly. Let's do, yeah. That'll be better. Okay, if we run that again, and then, so what I just did there is counter the number of heads and tails so that this updates, because otherwise it's just using whatever we had previously. We weren't updating it. So we've got 1 heads first, and so we're seeing that it's a lot more likely after our prior we update, we get a posterior where we add 1 to our uniform, which was 1, 1. And so we've updated it, and then we've got this kind of like weird wiggly line, which is our posterior, and it's just a bit confused basically, but it's saying, okay, we think it's much more likely at the moment that we get heads, 66% chance, and you can see where that comes from, right? 2 out of 3 gives us our mean. And this is our HDI, our 95% HDI, basically our credible interval. It's going from 0.21 to 0.99, so it's basically clueless. It's got no idea. It doesn't think that it doesn't think that the probability of heads is less than 0.21, which it well could be, right? It could just be really lucky. It'll be wrong some of the time, right? But you know, this is pretty good so far. And I can't remember what our true p-value is actually. What did we leave it on? 0.5. Okay, so this is meant to be uniform. So hopefully it will center the mean on 0.5 with a nice kind of tight HDI. And so we can see even now it's updated, and we've got a tighter credible interval. And so we've got 2 heads. Okay, interesting. Even though it's 50-50, we're seeing a little bit more heads. Fine. So this is pushing it up a bit, right? We think that the mean is 0.75, and we can see, well, 2 tosses is not really enough to know. We've got 3 heads. Okay, now we're thinking pretty much more likely that it's 0.81. 4 heads. Okay, we do get a tail. I was like, maybe we've got a bug in the code here. Let's actually go and double check our code just in case, because I think this is a bit unlikely. Yeah, we are using the correct. It was 0.5 last, wasn't it? Yeah, it was. Okay, so this is just a bit like unlikely, but what's happened is that we've got our credible interval closing in, weirdly high, right? And so actually, this credible interval is 95%. With 95% probability, we know this is true. This is actually the 5% time where it's wrong, right? It should actually include 0.5. And so this is a really interesting point to make, that even though it's 95%, there's 5% of the time that we'll be wrong. And so you might want to say, okay, if this is super important, maybe we're doing something on like medicine and we want to be sure that we're treating the patient with the right care, then you might want to have a higher percentage than this. You might want to say 99%, right? And that would definitely still include 0.5. And so we keep going. We've got no tails. We've got no tails. It's getting tighter and tighter and higher, and we're like, oh, this is wrong. But hopefully it will correct a bit. And so you can see already, right? Like we get a tail and then another tail. And so this is suddenly much better. Our 95% credible interval is now including 0.5 again, which is good. And so we keep going. It's not including 0.5 here. We'll keep going. And over time, you can see it's going to start coming down. And I haven't even looked at this ahead, but I know it will, right? And so we can see it's normalizing 0.61. It's including 0.5 again. And so over time, 0.58, 0.56, 0.54, 0.52, and it's done. And so in our 25 coin tosses, we actually get a pretty even split. Our posterior, you can see this graph is a little bit funky, and this is because of the way that we're doing it. Instead of calculating this posterior using the conjugate as we could, it's actually doing it with simulation. This is using MCMC, which we mentioned a little bit earlier, and I won't go into the details on that. But we can see that even for cases where we don't have like nicely behaving distributions, so in this case we do, but we pretended that we don't, we can still get some good results. And this is still quite wide, but we can see that it's updating at each point. We didn't know, right? I mean, 404 not found, a great guess, but 0.65 after 25 runs. Our model was predicting very accurately, and it still had a pretty decently wide credible interval. It wasn't very sure, but this is pretty good. This is pretty good, right? And the fact that we can say how certain we are, it's super useful. And when you're doing projects, which especially using more sensitive data, so maybe medical data or like engineering data, maybe you're doing something about like planes and you want to make sure that you're meeting like regulations on how secure it is, or maybe cybersecurity, right? You've got to meet some guidelines. You can use Bayesian stats to produce more rigorous decision-making evidence and information. And so let's scroll back up and then edit this a bit. So let's say instead that we don't want to run this every time. So let's say, okay, answer equals input. Ooh, more typos from me. And we'll say type y to type y to update posterior and skip. And yeah, fine, we're stripping it and we're lowering it. That's good from Copilot there. If answer equals, yep, and let's get that right. Okay, this is good. This is good. Perfect. So if we run this now, and let's say we want to run it with n equals 50, it's going to ask us at each point whether we want to plot it. And let's say we don't, right? And so this is going to be the same seed. So let's actually let's cancel this, and we'll have to escape from here. Okay, perfect. Let's reduce the delay as well to 0. So let's say the delay is 0. And so if it's going to do loads of flips, and we've hit 34 flips. Okay, let's plot it now. Let's plot it now. So, okay, this is pretty good. It's not massively tight, but it's 0.33 to 0.63, pretty good. I mean, it's obviously very, very close. That's great. Let's run it a whole load more times. Let's run it to like, oh no, oh no. Oh, we finished. What did I set it to run for? 50. Oh no, I should have done longer. No. Okay, let's run it for like 500. I mean, this is like really long. We'll see. And actually, let's change the true P. This is bad practice. You should go and change it where the actual constant is. Do not just but let's, yeah, I mean, we'll just do it. This is bad practice. And let's just let it run a whole load of times. So right now, hopefully, it's going to be thinking that the true p-value, the probability of getting ahead, is a bit higher. And it's going to give us a plot. Okay, 0.83, not quite perfect, but pretty good. It's thinking it's somewhere between 0.72 and 0.95. Yeah, that's true, right? It is 0.9. So let's run it a whole load more. Please run more. Let's run to like 100. There is a better way of doing this, but you know, I like having the manual control. Okay, and now we'll plot again. And hopefully this little demo is like making it really clear, like how this is working, what we're actually doing, and the importance of Bayesian stats, right? And this is a little bit wobbly, but actually it's looking pretty good. 0.86, not terrible, not terrible. Let's run it a lot more, right? Like at this point, you could probably be making a guess yourself, but you would have no idea how confident you are in that guess, not without calculating this by hand, right? And so using the Bayesian stats is allowing us to get this idea of how confident we are. And so we could run like a lot more. And if we just like spam this forever, I don't know what it's going to be at now. Half of the space will be going there, upper and lines even. Okay, we're at 255. So let's plot the posterior, and so we'll compare the posterior. So here we had a range of 0.79 to 0.92, which is a range of 13 or 0.13. And so we're hoping it's going to be less than 0.13, and we're hoping it's going to be accurate. And it will be. I'm pretty confident. Obviously, it's a 95% probability interval, so it could be wrong. It could be wrong. But as we increase n, the number of flips that we have, it's going to get more and more narrow and accurate. It's taking a little bit of time because of the model that we're using. It's simulating and not doing it. Okay, yeah, so this is 0.6. So this is shrunk to less than half of the size that it was. It's almost exactly right on the mean, and it's a much tighter, more confident estimate. So we're pretty happy with this, and we'll interrupt now because otherwise this will last forever. Great, okay, so I'm pretty happy with this. I'm going to clean this up so it's not like a million lines long in the notebook. We'll change that back down to like 25, and then we'll just shrink this. Okay, perfect. Right, and that's great. Cool. Okay. Now, are we kind of vaguely happy with this? I'm hoping that we are. I'm just thinking we could. I know we loaded the Titanic data earlier. We could skip it and. No, let's do it. Okay, so what we're going to do is we're going to say, right, let's try and work out the likelihood based on whether someone is a man or a woman for the Titanic data set, whether they survived or not. And before looking at the data, we're going to have a prior. We might think that, you know, you might think one way or the other, right? You might be like, well, maybe you know, the kind of like biological advantage of being male is strong enough that they're more likely to be able to swim and save themselves, so maybe their survival rate is higher. You might also say, probably fairly sensibly, and if you know much about the Titanic, you might say, well, maybe women got on the lifeboats first, and that gave them a big advantage. So you might have a prior in either direction, but let's have a little bit of an exploration. So first of all, actually no, I was going to say let's look at the data and have a little think, but let's not. So do we have our data frame loaded? I think we do still, right? Yeah, we do. Okay, so this is our data frame. It's just df, and let's do some stuff with real data. So perfect. Yeah, what we're basically just going to be doing is some plotting, and so any suggestions for a prior to have here? So remember, it's going to be an alpha prior and a beta prior. Do we think we should have it uniform? Does anyone think, okay, maybe one way or the other? let's say for the sake of argument, that maybe men were more likely to survive. 2-to-1 for women, so women are more likely to survive. Okay, yeah, that's cool. That's cool. So I think the way we're going to do this is we will write. Let me get this right. So yeah, let's look at the survival rate just for women for now. I think this will be simpler because we've actually got like quite a lot of variables otherwise, and this is maybe going to get complicated. So let's take the suggestion from 404 in the chat and say that the survival rate for women is going to be 2/3, right? So 2-to-1, 2/3. So 2 for every 1 woman that doesn't survive, there's 2 who do. So we could say that as 2-1, right? And that's pretty uninformative. We could be like more confident and say 2010. And let's be a bit more confident and say that. Let's also actually spoil it a little bit and first calculate the actual survival rates, because we're going to need this to do the conjugate update. So we're going to do that by, let's just call it survival, and we'll do a cross tab. So we will do pd.cross tab. And this is going to basically allow us to condense our dataset down into just, I think we need a capital S. You can check the variable names for yourself, but I'm pretty sure these are right. If they're not, we will check them. But I'm pretty sure it's, oh yeah, we actually got them here, survived and saved. Okay, yeah. So we are right. That's great. And then we'll just, okay, so we made a little table. You can see that 233 women survived, 81 didn't. So actually this prior is looking pretty good, but obviously we can't update the prior now that we've seen some data. That would be bad practice. And way more men didn't survive than survived. So that's interesting. So let's say our Bayesian question is, what is the true probability that a randomly chosen female passenger survives, right? And so we've got our prior, and then let's say the number of successes, we'll call it like heads, right? So we'll say H. We've got a total number of trials. This is like our flips, right? So you can be connecting these up already. So we've got 233 heads, if you like, so people who survived. And then our total number is going to be 233 plus 81. So if anyone wants to do the maths on that, let's do it quickly. 233, 310, 314. I want to say 314. Yeah. Look at that maths. Beat Copilot, that's for sure. Okay, so we've got our priors. Let's maybe do some labeling priors. And this is basically our data, to be honest. We've taken this from our data set. And so let's just do some plots. Let's do some plots. So we will maybe plot our prior here. So let's say plot prior. We can see how our prior updates using this conjugate update. And this is using real data, like I said, hopefully in a super cool way. And then after this, I think actually we're going to run out of time to do the final bit of the demo that I really wanted to do. So what I will do is probably just copy and paste it in and talk through it, because I think it's a really cool and interesting demo. And it's nice and interactive, so we can make a little game of it ourselves. So we're just making a plot here, and we will do the same as before. Plot our data, and does this look right? Yeah, this looks right. Okay, yep, perfect. It's even got a label for us. Awesome. So Copilot's saving the day here. And then we want some labels. So we will say, what is next label? Probability of survival. And then we will do plot y label density. Yep. And then we will do a title. Prior distribution of survival probability. And then we'll put in brackets female. And this is pretty good. Okay. And then let's update. So let's do this conjugate update. So remember, for the beta binomial conjugate model, basically just conjugate, just meaning they work nicely together, we can just add the number of successes and number of failures to each. So our posterior is going to be basically our ratio that we decided earlier is just updating with the data that we see. So this is like our heads, adding on the number of heads, adding on to the number of heads that we kind of expected to see in the ratio that we set for otherwise. So this, in this case, the number of failures or people who didn't survive is going to be n minus h. And remember, this is also equal to tails in the examples that we did earlier. So this is kind of quite similar. And then we will plot it again. So we will do x equals in space again in the same way. And hopefully it's just going to do lots of nice predicting for us. This is what we want. Vertical line at the posterior mean is what we're kind of hoping for. Yeah, so this is actually the equation for the mean here, and am I happy with that? Yeah, I'm happy with that actually. So let's finish this off. Yeah, okay, perfect. So this is the equation for the expectation of a beta distribution, and you can Google this. If you Google beta distribution, there'll be this equation. It will say alpha over alpha plus beta is your expectation. You can also calculate the variance and lots of other things using this. And yeah, you're welcome to do that. I recommend, if you do genuinely want to get into this kind of statsy stuff, which I love personally, playing around with data sets, playing around with distributions, all of these things are good things to do to really nail the understanding and your intuition. Because I think it's only by playing around with real examples that you can actually build a good, like I say, a good understanding. So what we're doing here is we're going to try and get the credible interval, and instead of simulating this time, you see again, we didn't sample simulate to get our mean. We're not going to do that either here, because like I said, there are nicer ways of doing it. These are not the ways that I would do it using R. R is much nicer for this. I don't want 0.5. Why did it suggest 0.5? What we need actually here is we want CI low and then CI high. So we're getting our these are our bounds for each of these for the credible interval, that is, and we, like I said, we could do this through simulation and sampling, but instead we are going to do it analytically from the actual distribution itself, which you can do here when you have the distribution fully described. If you only know the distribution up to proportionality, so if you remember in the notes, we had that little proportional symbol, the posterior is proportional to the prior by the likelihood, you wouldn't be able to do that. And that might happen when you've got some nasty distributions that are hard to work with mathematically. Calculus might not cut it, and so you might only know what your distribution is up to proportionality. So there's a constant missing. You don't know what the constant is. And you can fix that using simulation, which is nice. So we love that. We love that. We love that. We love that. Right. That's got an extra bracket on, and then that's perfect. Okay. Now let's label our axes. So probability of survival, probability of density. Yeah, fine. Let's speed through this. Doesn't matter if it's not perfect. Got the legend. Sure. Height layout. Show. And then let's just quickly print our stats. Posterior mean, perfect, and then our credible intervals. Okay, so awesome. Look at that. So what we've got is we've got our prior, and this is like 404 shouted out. We're basically saying, okay, we think it's more likely that someone survives than not survive when they're a woman, at least. Yeah. Looks like we were kind of on the money, not quite right. Our posterior mean ended up being about 0.735. We've got a good credible interval. This is interesting. So before seeing our data, we had this kind of idea, and then, but maybe let's say we were like, oh, actually, I don't think I think more women will die than survive, because it's Titanic's in the middle of nowhere, and it's really hard to swim anywhere, and so on. There won't be enough lifeboats. So we might start with this prior down here, and we can see that even with a prior that's not quite right, we can update to the correct result. And we've got almost exactly the same thing. Certainly our credible interval includes the right result. And so it shifts it. You can see this transformation from our prior to our posterior. We're updating our belief. using the data. And so unless we had a really, really strong prior, so we could break this, right? We could say our prior is like really strong, like really big. We think there's no way that this is wrong. You will see here that actually our prior was very, very confident, very narrow, very confident. And what that's done is it's brought the posterior all the way down. And so you can have a very informative prior that sways your outcome, right? And you need to think about this when you think about, okay, how much data do I have? Like, how confident am I when I'm setting my prior? Like, is my prior too informative, right? Because in this case, we might as well not even use the data because our prior is so confident. And so you've got to be careful when you're setting your priors to set them to something reasonable, right? And so, like Oracle suggested, a reasonable prior, we're thinking, okay, more women than not survive. They've probably got on lifeboats. That's pretty good. We're not super confident, right? We've got pretty low values here. We could even make it less confident. And this allows more of the data to do this stuff, right? And you can see here, like, this is very, very uninformative prior. And so this is what we originally had. We could even just say, okay, we've got no idea, right? We've got literally no idea. Let's just make it flat. And so you see this is what I was talking about when we had this uninformative flat prior. Yes. So if we start with wrong but uncertain assumptions, Bayesian stats can help us get closer to the true value. Exactly. Often what you will do is you will start with uninformative priors. So something more flat, something a little bit softer, right? Like you might start with, like, you know, your gentle kind of, like, you know, 6 to 3, right? You might be like, okay, I'm like gently thinking that this is true. It's somewhere in this range. I'm pretty confident with that. You're basically narrowing down. You're saying it's not going to be down here. Then that's pretty common as well. And you can see this is getting good results. So hopefully that's really neat. Yeah, we could use this to compare two groups. I'm just looking at the time. We've got 15 minutes. Let me have a little quick check of what I think would be best to do here. Are there any opinions on what we want to do? Do we want to do something a little bit more like gamified and practical, or do you want to keep looking at some theory? So we've got a question in the chat about is it the alignment between the means for the prior and posterior? How do we read the chart and interpret good results? So I guess this, I mean, you put it in quotation marks, which I think is a good thing to do, but like, what is a good result? Do you mean accurate? Do you mean certain? These are also questions that you should have. I would suggest that a good result is one that is, like accurate and informative, but also not overly confident. And so, like, this is a question, right? This is a question that you can have, and people often have, right? People will be like, okay, well, your Bayesian statistics have said this is the case, right? So a common example might be like medicine, right? Let's say that you've got, and this is a classic example, you've got some patients who are, you've taken in for testing, right? You've got a disease that's very uncommon, maybe 1% of the population has this disease. And you know the sensitivity of your test. So maybe your test says, okay, if this person has the disease, 99% of the time, your medical test, like your COVID test, will tell you 99% of the time that they have it, if they do indeed have it. And so what you've got is you've got this conditional probability. And let me pull up. So typing maths is always can be a little bit harder. I don't think I can do this very easy. Give me 1 second and I will find a nice example online. Okay, let me, you know what? I can quickly drop some. I'm gonna make a quick markdown file and then we'll talk through it. Okay, no, this is not going to be quick to do. Okay, I've changed my mind. We're not going to do that. What I will do is find, like I said, a quick image online or something. Yeah, okay. So, let me share my screen. Not that. Stop screen. We're kind of towards the end as well, so we can take things slow. I will do a quick demo to end. Okay. Perfect. Let me, okay. Okay, so this is maybe a nice formula. It lets me see it in big. Okay, yeah, I don't know, this website looks okay. Yeah, so this is nice. This is Bayes' theorem, right? This is basically what we've been using. And we discussed it a bit, but what you have is you have your posterior, which is this here on the right-hand side. And then you've got your prior here, which is some idea that you already have, right? This is distribution. And then you've got your likelihood. And so actually this down here is called like your normalizing constant. And it's actually the probability of E in this notation. And so, like, for example, you might have actually your H here, your hypothesis is that someone is positive for COVID, okay? And your E, your evidence might be that you've got, let me get this right. Yeah, that you've got a positive test result, right? So your H is, okay, they have COVID. What's the probability that they have COVID, given that the test was positive, the COVID test was positive, okay? And this is conditional probability. This is kind of like the foundations of theory, really getting to the grit of it now. And in this case, right, what we've got is, okay, so what's the probability that we have COVID given we tested positive? And you can work this out by saying, okay, it's the probability that we tested positive, given that we had COVID, the other way around, right? Multiplied by the probability that we have COVID. So the probability that you have COVID is pretty small, probably. Most people didn't. You know, like, oh, well, okay, COVID is maybe a bad example because loads of people had COVID, but like maybe like HIV or some like uncommon disease. And then down here, this is actually just a way of expressing the probability of it getting a positive test in general. And again, this is just broken down. It's using the partition theorem, but the crux of it is basically that we can use the prevalence of a disease and the knowledge that we have about our test, how good our COVID test is, to accurately say, okay, does this person actually have COVID or HIV, given that they tested positive, right? And this can be pretty important. And this is like really strong in the sense that you can use this, you know, disease testing in medicine to produce statistically rigorous results. The frequentist approach wouldn't use a posterior and it wouldn't use a prior. It would just say, okay, let's use our likelihood, right? Which, let me get this the way around again, but this would be like, okay, what's the probability that the test is positive given that they have the disease? And, you know, you could use this, but you like you said, the question is kind of like, how do we know that our results are good? How do we interpret that they are right? And it's basically only in retrospect that you can do this, right? So you could build a Bayesian model to do stock prediction, and you wouldn't know it's right until after the stocks have changed. In the same way, you might build a model for like detecting disease, and you wouldn't know until you see the data later, right? And so there's this really nice thing about Bayesian stats that you can have this prior, and then you update it using your data and your likelihood, and you get this posterior. And then you use your posterior as your next prior. Then you update it again with your likelihood and your data, new data that's come in. Then you have a new posterior. And so there's a saying that today's posterior is tomorrow's prior. And it's the idea that you can constantly keep updating your beliefs based on the data as it comes in. And so it's hard to say whether it's good or not, but future data will verify your findings. And like we said earlier, right, when we were flipping that coin at the start, we've got not very much data. But at least, right, if, you know, it might be wrong in the beginning, but as we update more, we're basically, what we're doing is we're taking the previous posterior and using it as our prior and updating iteratively. And in doing that, we can, produce more and more kind of accurate results. And I guess what you're really asking is like, how do we know when they're accurate enough? And that's going to depend on your context. But what we do know is that as we do more and more of this, we can see our credible interval shrinking. And that means we are more certain. And so, yeah, as long as your credible interval, maybe you want it to be a 99% credible interval instead of 95%. But as long as you are happy with the statistical significance of your credible interval, i.e. that, a 1%, like a chance of 1% error is acceptable, then you just do it until it's narrow enough that you're happy, right? And so that's how I would suggest you kind of interpret these things, is by just iterating until you've got a narrow enough credible interval that you can be confident that you are certain enough. So yeah, this is kind of like Bayesian experimentation, Bayesian modeling, Bayesian methods as a whole. And so what we're going to do now is I'm going to share my screen. I built a Streamlit app in advance, and we will run it pretty fast. I actually haven't tested it very much, so we're going to hope that it works. But what it's using is something called Thompson sampling, which is like kind of a very simple reinforcement learning agent, but it uses posteriors. So it uses the posterior for different actions that it could choose. And it says, okay, which one of these makes this next thing the most likely? And that way it learns, basically. Hence reinforcement learning. So we've got maybe 8 minutes. I will run this now by showing it on my screen. Okay, so this is our code here. See, I've done some experimenting over here, and it's just like a basic Streamlit app, and I'll talk through the theory of how this works, but maybe it's helpful to demo it first. So what I've set up is using create click streams. So the premise of this is, let's say you've got some banners and you want to check the click-through rate, basically how likely someone is to click it and go to like a partner page or something. And here we've got the probability that someone would click it based on banner design A as 0.9, banner design B is 0.4, banner design C is 0.3. So maybe you've got 3 different banners and you think, oh, I want to learn which one is the best banner to show to users to get the highest people visiting my site for, like, advertisers, for example, right? So this is a really practical use for this. So we ran this to set this initially, and then we've got this little Joule app, and so we can run it with Streamlit run Bayes banner Joule.py, and it's going to open in another window, which I'm not sharing, so I'm going to swap my screen over. So give me just 1 minute. Okay, it's not running properly. We'll very quickly rerun. We got time. Let's make a new terminal, just in case it's that's the problem. Okay. Perfect. Okay, and let me share it to you all now. Perfect. Okay, cool. Okay, so hopefully you can see this. Like I said, it's a very Streamlit. It's a very simple Streamlit app, and what we've got is we've got an agent which is using Thompson sampling, and maybe it's helpful for me to talk through how that works first. Just finding it in my notes because I wrote it up in a nice and intuitive way. Or maybe I didn't. I thought I did. Okay, yeah. So it's like a 4-part algorithm, and the way that it works is for each of these options that we have, we've got 3 different banners, like we discussed, and we know secretly that A is the best. But let's say we don't know that, for example. And this agent's trying to work out which banner is best. So it's got to do some exploration, right? If you come across reinforcement learning, it's got to do some exploration, but actually it's also got to do some exploitation. It's got to pick the best one to get as many clicks as possible to our advertiser or whatever, right? And this is like a simple example, but you could use this in a bunch of different ways. And so what it does, it has a posterior for each arm's success probability. So like the survival or death, or the heads or tails, right? We've got success, either a click or no click from each of these banners. And so each time in this little game, we're going to serve a banner to 2 visitors based on the one that we click and the one that the agent clicks, and we'll see who gets the better score. And we won't beat the agent unless we cheat and we use A all the time, but we won't be there. So what it does is it samples from each posterior, it picks a value, and then whichever value is the highest, it will play that. Which means that, if by chance it picks a lower value in a more confident posterior, it will still do some exploration, but it will very quickly kind of normalize to the right arm of this or action, right, of this problem. This is like a bandit problem or like a multi-arm bandit problem. It's like a very foundational reinforcement learning challenge. And so this is also a bit like A/B testing. You can do A/B testing and use Bayesian modeling to do that as well. That's very common too. So let's pick B and we'll see what happens. So we picked B and we got no click. Agent picked B and the visitor that they were served to did click. So they're already beating us, which is a bit sad, but that's just luck. So we'll keep running it. We're going to stay on B, and you can see here that these graphs are updating. So the agent's posterior beliefs are down here, right? These plots. And so if we keep clicking through, we're not going to do very well because we're picking B, which is not as likely as A. But you can see already that it's pretty confident that A is great, right? It's pretty confident that C is bad. And if we just keep clicking, it's getting, like, you can see the curve here now. It's not even really bothering to check C anymore because it just knows that A is so good. The likelihood of it being C being better is basically impossibly small. And you can see it's getting way more clicks than us. It's doing much better. We've only clicked B, right? And it's decided that B is not as good as A. So this, hopefully, I think is like a really nice example. Like, we can just keep spamming this and it's going to keep beating us until we pick A. And then it should kind of like, we should catch up a bit, or it needs to not catch up, but get similar results. So you can see we're gaining much quicker now, but even so, it's decided, okay, like roughly the peak there is at 90%, which is, if we went back to our results, our little script, the probability that we set with A. So maybe an interesting example would be, let's update all of these. I'm going to do it behind the scenes and then just refresh. Let's update these. So A is 0.4, B is 0.6, just to show that this is actually really working. Yeah, B is 0.6. Actually, wait, no, I'm going to update these and I'm not going to tell you. You just have to guess. We've got a minute. Oh, maybe we don't have time. Okay, maybe no guessing. Maybe no guessing. But I'm going to make them much more similar, and then I'm going to run that. And then we will rerun. We will rerun this. So I've called this Bayes banner duel because you can kind of compete against the agent and probably lose. Let's open it up again, fine. And so now I think, what do we say? So C should be best. So let's pick B. I think B is the worst. Let's pick B and we'll just spam the spot. While I'm wrapping up, this is basically it, by the way. This is kind of the end of the session. We run out of time. So if you would like to give feedback, please do. I think the link is mlh.link/GHW feedback, I want to say. And I am basically out of time. So we'll just spam this. And we'll see. It's picking C. It really loves C. It's not even really bothering to pick B or A, and it's correct, right? It is correct. Immediately, it's really confident in itself. It's getting really high clicks. This is, I think, pretty impressive, and it shows you the power of like using Bayesian methods in decision making. So yeah, if you want to learn about this more, you're looking for Thompson sampling, and yep, I did beat you to it, but the link is in the chat. Thank you for sending that. And with that, I'm going to wrap up. I'm very wary of using up whoever else's time is next. I don't know who. Oh, it's Stay in Globe Hack Week. So head along to that. Should be really good. Learn about what's coming up next. And thank you very much for joining me. All right. Bye-bye.